All right, here is your lesson on transformational geometry. Wow, that's a mouthful. Let's get started. Well, I like to play Tetris. I'm going to play some online Tetris to get me started here today. All right. All right. Okay, I need to translate, rotate, translate. All right, that's about enough of that. I could play that all day. Very cool, very cool. Okay, here we go. Transformational geometry. Get out your notebooks, make a new page, and write this down in your notes. Starting with transformational geometry, April 28th, 2020. And obviously pause the video when you need to in order to get all these notes written out. But I'm going to be moving through fairly quickly, so just make sure you're using the pause function on your computer or tablet to stop and write these things down properly. So today's lesson objective is to be able to perform a translation, rotation, and reflection, and a combination of all three in the first quadrant of the Cartesian plane. So that is a whole lot of information, and I'm hoping by the end of today's lesson that you will at least understand the vocabulary of this of transformational geometry. And then in the next lesson, I'm hoping that we can start practicing using some of these math techniques. So today, this is about taking notes and understanding the vocabulary. The next lesson I'm posting in succession is going to be about practicing how to use these different terms. So let's get started. So make sure you write down lesson objective, and then make sure you write down prior knowledge, and then make sure you write down vocabulary. And I need to turn off my notifications. 1 second. Okay. So, prior knowledge, plotting ordered pairs and angles, and vocabulary. Here are the terms: polygon, congruent, translation, rotation, reflection, and prime marks. Those are the terms that I want you to learn. Okay, so going back, here are the curriculum outcomes that we will be focusing on. There are 2 of them. Today's lesson is just about the vocabulary. The next lesson will be the actual curricular outcome. While you're practicing them, if you're able to perform them, then you are meeting that curriculum outcome. So let's get going. So here is a tile mosaic of a whole bunch of different polygons that are arranged in a design. Well, this is exactly the type of design that you can create using the mathematical knowledge that we are gaining from today's lesson. These are congruent polygons, these triangles right up here. They're both right triangles that have been translated this one has been rotated into this position. So once we talk a little bit more about the outcome, you will see exactly what I'm talking about when you move these shapes around. So first thing we're talking about is polygon. What is a polygon? Well, up here, here's the definition. It is a 2D closed shape with straight lines. 2D closed shape with straight lines. So you can write that down in your notes. The first note underneath, you're going to write down polygon. It is a 2D closed shape with straight lines. Okay, so you can pause, write that down. So based off of that definition of these, which ones are polygons and which ones are not? So I'm going to give a check mark to the ones that are and an X to the ones that are not. So is this a polygon? At home, you can say either yes or no in your head or out loud. If you said no, you are correct. That is not a polygon because it does not have straight, or it has curved lines. Is this a polygon? Yep, that is a polygon. It's all straight lines that are connected by vertices. and it's a closed shape. Is this one a polygon? No is correct. How about the heart? Is that a polygon? It must be. It's a shape. It is not a polygon. It has curved lines. Is this a polygon? Yes. Straight lines, closed shape. Is this a polygon, this triangle? Yes. Straight lines, closed shape. How about the circle? That's a closed shape. It doesn't have straight lines. What about this quadrilateral? Yes, that is a polygon. Straight lines, closed shape. How about this check mark? That is a polygon. Okay, the next thing we are talking about is congruent. So, congruent means a shape identical in form. So, go back to your notes and write down congruent. A shape that is identical in form. And now on my notes here, they have the two shapes. Those are equilateral triangles that are labeled and rotated about that point there, as you can see, but they are identical in size and shape. So that is congruent. I'm going to talk a little bit more about prime marks later, but I also labeled it with prime marks here. Okay, so make sure you put those notes down. I'm going back to the original page. Congruent, a shape identical in form. So these two here, are these congruent? Yes, that is an exact copy of this right angle triangle. They are the exact same, congruent. Just because they are moved away from each other doesn't change anything. They are congruent. So let's take a look at these two. Are those congruent? They are not congruent because one is larger than the other. How about these two? Are these congruent? They are not congruent because one is larger than the other. How about these two? Are those congruent? If you said yes, these are congruent because they are identical in form and they're the exact same size. They're a copy of one another. That is what congruent means. Moving on. We are going to focus on slide, turn, and flip. Those are the old ways of saying things. That is just natural, casual vocabulary. We are now learning the mathematical vocabulary for transformational geometry. So slide. When I think of slide, I kind of think of curling and how a rock slides across a sheet of ice. Well, that's no different than what we're talking about here in geometry. Instead, though, instead of a curling rock, it would be a polygon sliding across the first quadrant of a Cartesian plane. And if you did ordered pairs, you know what I'm talking about in terms of a first quadrant, and you know what I'm talking about in terms of the Cartesian plane. But we're no longer using the word slide. We are now using the word translation. So slide means the same thing as translation. So we are translating polygons across a Cartesian plane. So what does that look like? Let's first write that down in our notes. And I know I haven't talked about prime marks yet, but you should write down prime marks also. Prime marks represents how many times a vertex changes its coordinates. Okay, so that's a prime mark. And translations slide when a shape is slid across the Cartesian plane up, down, left, and right. So that is what a translation is. Okay, pause the video to write that down, and now I'm going to give you some examples. Okay, so here's a translation. When a figure is slid in any direction. Okay, so I said up, down, left, and right because that is what we're focusing on in grade 6. But a translation technically means it could be slid in any direction diagonally. But what we're focusing on is not these, not diagonally. We are focusing mainly on translating a shape up, down, left, or right, or north, south, east, and west. Okay. So translations. I'm going to go through what a translation is and what a translation is not. So I already had my answers already put here, so I'm going to move them back. All right, so let's take a look at this green square and this green square. Is that a translation? Well, you might be thinking, yes, it is, but it's not, because in order for it to be a translation, it needs to be congruent. This needs to be an exact copy, and unfortunately, this square is much smaller than this. This square is much smaller than this square, and therefore, it is not a translation. Eh. How about this one? If this square, purple square, translates to this purple square, can that work? Are they congruent? Yes, they are. That is a translation. This square can move to this spot. That is a translation. It slides down. And it slides down 1, 2, 3, 4 spots. Okay, how about these? Is that a translation? Well, if you've already classified it as non-congruent, then you are correct. It is not a translation. How about these right-angled triangles? Well, it looks a little bit funny. They don't look like right-angled triangles, but that's because they're rotated a little bit. But yes, that is a translation because they are congruent. But watch. I take this vertex, I move it over 1, 2, 3, 4, 5, 6 spaces to the left and 1 space down. It has now become this triangle, right angle triangle. That is a triangle. Ding, 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 ding. That is correct. Okay, let's take a look at a couple other things. Now, how can we tell which one is the original and which one is the copy? Well, that's where prime marks come in handy. So this is how we use prime marks. And here is our definition back on this page here. A prime mark represents how many times a vertex changes its coordinates. So let's take a look here. This polygon, right angle triangle, is translating to become this polygon or right angle triangle because they are the same triangle, they just translated to the left. Now, the coordinates changed once as per the directions. So my directions would be translate this triangle ABC 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces to the left. So I'd say translate triangle ABC 10 spaces to the left. And then it becomes this right angle triangle. And in order for me to show which is the original and which is the copy, I have to put prime marks. So now this vertex moved from here to here once, so therefore I put 1 prime mark. So A1, B1, C1. And that shows a complete translation. Moving on. Here we have another polygon, and it is polygon ABCD, or a rectangle ABCD. And I have to translate that particular rectangle. Let's see what that looks like. Well, it translates which one's the original, which one's the copy. So think about that in your head. Which one's the original, which one's the copy? Okay, if you said that this one is the original, the one that I'm circling right now, then you are correct because it doesn't have the prime marks. So I would give the direction, translate rectangle ABCD 1, 2, 3, 4, 5, 6 spaces to the left and 1 space down. It becomes rectangle A1, B1, C1, and D1. That is a complete translation. And it shows the prime marks. And now, to move it again, it would go, okay, let's translate that rectangle A1, B1, C1, and D1 to this space. Actually, it's not. To this space, I would say translate it 1, 2, 3 spaces to the right and 1, 2, 3 spaces down. And now it shows it started as the original. The first directions told me to translate it this way and down, Now the next directions told me to translate it 1, 2, 3 spaces to the right and 3 spaces down to finish up or finalize in this spot here. And that is now where our shape ended up. And it shows that as double prime marks. So it's now A2, B2, C2, and D2. And that shows that that is the final location of where our polygon ended up with translations. Let's take a look at another. So here's some directions. 3 units to the right and 2 units down. So you can say units, spaces, spots, but in this case we're going to go 3 units to the right and 2 units down. So where would that end up? Well, let's take a look. Let's count. I'm going to move this vertex triangle ABC 3 units to the right. So we go 1, 2, 3 units to the right, and then 2 units down. 1, 2 units down. So now this vertex A is going to end up right here. So I'm going to copy that, and that would then show it 1, 2, 3, 1, 2, right here. But now how do I know which is the original and which is the copy after the directions? I need to add my prime marks. So I will do that. Prime mark 1. So there we go. My translation is now complete. So that is a translation. Those were the examples on how to do a translation. The next thing we are going to look at is rotation. And a rotation, we used to think of it as turn. It's when something turns. Well, my dog knocked down my green screen. She laid on it. Anyways, a rotation is a turn. So that was the old terminology, turn. It is now, we're going to think about turns as rotations. Slides are translations, turns are rotations. So going back to our notes, we are going to write down rotation. As you can see here, it's a turn. When a shape turns on its vertex or axis. So when a shape turns, rotates on its axis. Okay, very important to remember that. So that is the next part of our vocabulary. Make sure you write that down, and I will give you some examples. Okay, rotations are figures that turn about a point or vertex. A rotation can be clockwise or counterclockwise. So we can write that in our notes as clockwise, CW, or CCW. So rotation, you can say clockwise, which is CW. Oh. Okay, that's working. And clockwise is the same direction as a clock. So you can put a circle with an arrow. And counterclockwise, which is counterclockwise, which is CCW. And you can put that the opposite direction of the way a clock goes, which is that way. Okay, so write that into your notes. I just wanted to add that. I forgot to put that in there earlier. Okay, the turn is described and can be described as a fraction or as a degree. We are going to be talking about it as a degree. We're doing our rotations as degrees, hence why we needed to learn angles before we could do this. So let's take a look. Here's clockwise, here's counterclockwise. You might want to put that down in your notes. Actually, you for sure should put that down in your notes. Okay, a 1/4 turn. Oh, sorry. A 1/4 turn or a 90-degree rotation is the same thing. So a 90-degree rotation is a 1/4 turn. So turning a shape 90 degrees is 1/4. A half turn is the same thing as a 180-degree rotation. And a 3/4 turn is a 270-degree rotation. So we learned about this in our angles unit. And I just wanted to show you something to bring up what we did with our reflex angles. We talked about going beyond. So here are your rotations. We have a 1/4 turn, which is your 90 degrees. which is going out east. So we take the shape and we turn it 90. We have the half turn, which is 180 degrees. Then we have the 3/4 turn, or a 270-degree rotation. Okay, so remember we talked about that with our reflex angles, and I'll go into a little bit more detail when we start doing rotations on the paper. But for now, actually what I'm going to do is I'm going to screenshot this page and I'm going to put it into our lesson because this is a good one to remember. Snip. And I'll put that into our video lesson so that you guys can remember. Okay, moving on. So here we have a shape that is going to be rotating. So we have a isosceles triangle, and it is named CAT. Haha, how funny, cat. The cat triangle is going to rotate, and it's going to rotate about vertex A. So point A, this vertex where these two rays meet, is how this shape is going to rotate, and it is going to rotate 1/4 turn or a 90-degree turn clockwise. And what that looks like is this. So that shape just rotated 90 degrees clockwise about point A. So make sure that you would put down your point on A, then C would go end up over here, and T would then end up here. So that is one rotation 90 degrees clockwise about point A. Okay? So this is the same thing as a compass rose. It's the cardinal plane, north, south, east, and west. So just to help with directions. But so rotating this polygon MATH, math, 180 degrees clockwise about point T. So here is your vertex that you are going to rotate and do a half rotation. Where is that going to end up? Well, let's find out. We're going to start with MATH, and then it is going to rotate. There's 90 degrees, so half of 180. So that's where it would end up there. And then there's your 180-degree rotation. So now all of a sudden, our shape ends up pretty much rotating clockwise all the way around 180 degrees, that the top part of it is now on the bottom. And T still seems in the same place, so we actually don't add prime marks there. But H now is over here, M is over here, and A is over here. And the only thing I'm missing from this slide here is because that is now changed, is these need to have their prime marks. Okay? T does not get prime marks because it did not change its coordinates. Just a fun fact for you. Okay, rotate this triangle 90 degrees counterclockwise about point A. So we are rotating on this vertex 90 degrees. So it's a 1/4 turn counterclockwise. So it's going to go this way. And that would look something like, well, I won't exactly be able to show you here because it doesn't give you enough space. But to give you the idea, it would rotate B down over here. A would still stay in the same place, and C would actually end up in this position here. That's where C would end up. Okay, and this one, 90 degrees counterclockwise about point Z. Well, here's point Z, and it's a 90 degree rotation, which means it is going to be this way, and it's clockwise. Sorry, I thought I said counterclockwise. It's clockwise. It's going to rotate down this way. So meaning W is going to end up in this spot here. Y, and I'm just going to count the amount of spaces down. So 1, 2, 3, 4 spaces. It would end up being here instead. So W would be here with 1 prime mark. Z doesn't get any. X would then be here in this spot here with 1 prime mark. And then Y would be in this spot here with 1 prime mark. And it would then draw in the shape here. And that's how that rotation would work. 1/4 turn. And that is where your polygon would end up. Okay, so that is a rotation. And the last thing that we are going to talk about today is a reflection. So I'm going to go back up here and we're going to go to a reflection. So in your notes, you're going to write down a reflection is a flip when a shape flips over a line. So it flips over a reflection line. And you can add to your notes here. Reflections are done across a line of reflection. So here is a line of reflection, and it literally flips over top. So this corner becomes this corner. It flips upside down. The figure and its reflection are congruent and face opposite ways. So this was up, and it's now facing that way. They're facing opposite ways now. So this was facing this way and is now facing this way. Okay. The line of reflection can be any direction. So a line of reflection can be diagonal. It can be up and down. You just have to flip it across the line. And the figure and its reflection image are the same distance from the line of reflection. So what that means is this distance from here to here is the same as the distance from here to here. That's the same distance between the two. So it's basically just flip it over, but make sure it's the same distance away from the line of reflection. So let's take a look at a couple different examples of that. Okay, using dot boards to help you choose which image would complete the reflection. Unfortunately, you don't have dot boards, but let's take a look. Thinking about it, okay, I want you to choose either image A, B, C, or D, and which one you think would be the correct choice for reflecting this image across. So think about it. Is it A? Is it B? Is it C? Or is it D? Okay, if you chose B, you are correct. Now, when I'm reflecting it, do I put it right on the line? Nope. Do I put it 2 spaces away? Nope, because it's only 1 space away from there. I have to put it the same distance, and it reflects exactly as if I'm flipping it over. So this side becomes this side. They now face the opposite directions, as we talked about before. That is facing that way, is now facing that way, because it flips upside down. This point becomes this point here. It flips upside down. Okay, that is a complete reflection. So this triangle here, how is that going to reflect over this line of reflection? Well, we need to flip it over. So we have, it would be one point here, then it would be 1 point here, because it's the same distance across, and then 1 point here. And then of course we fill in our lines. And I'm just going to do a basic line here. So we have our triangle. Actually, I should have just done a shape. Fill it in with blue, just like this one. So there you go. So there's our triangle. And our vertexes are labeled D, G, O. Now that's important that we understand which ones become which. So O, if we're reflecting this, G is now going to face the opposite direction. So that is now G. It's not, because it's flipping over. And then this is now O. And we have to put our prime marks in because it changed coordinate places. And D stays in the same place. So that's D1. So G goes flip and becomes over here, over the line of reflection. So that's how you do a reflection. Okay, so there's the answer. I guess I should have just went one slide instead of doing it myself, but as you can see here, there's my prime marks. There is my reflection. Okay, so this is now a line of reflection that is horizontal, parallel with the x-axis. So how is that going to work? Well, it's 2 spaces away, which means our polygon is going to start here, and it starts here because we have 1, 2, 3, 4 spaces in between. And I'm going to get my shapes out. I'm going to get my rectangle. I'm going to get yellow, and I'm going to draw this one in right there. So there's my reflection over the line. It's 2 spaces away. It is going to go, W is going to reflect all the way down and become this point here, as you can see, because it would flip over the line and become this point here, meaning this is going to be Z, this is going to be Y, and then this is going to be X, and this is going to be W, and I have to put my prime marks in to show the reflection, and I am done. So I reflected that over the line. Let's see if I got that right. I did, except for it didn't write in my, it doesn't give me the letters, but yes, I got that right. Ha. And then of course, this is a double reflection. This is tricky, so I'm going to actually skip that one. Okay, so we talked about all the different things. We talked about translations. We've talked about rotations, and we talked about reflections. So slide, turns, and flips. Slides are translations. They move across a coordinate, slide across a coordinate plane or a Cartesian plane. Rotations turn a polygon about a point, either counterclockwise or clockwise. And reflections flip a polygon over a line of reflection. Okay, so at the end of all this, this is basically for taking notes. It is an introductory lesson on how to do this, but I'm now going to go back and play a little bit of Tetris. So let's take a look and see if it means anything else to you now that we've learned a little bit about transformational geometry. It's really loud. Just a sec. Resume. 3, 2, 1. Okay, so I'm going to translate down. I'm translating down. This polygon is translating down. Now, oh, it doesn't show it, but if I count these spaces, I can tell you exactly how many spaces I'm translating down. Of course, it's blocking my coordinate grid, but Tetris is a game of transformational geometry. That's all Tetris is moving polygons across our Cartesian plane. So I have this different polygon, and I am going to rotate it, translate, so I'm rotating, translating, translating down. Translated left, translating down, translating down, translating down. Okay, rotation, now translation. Okay, I'm just going to translate this one down. This one, I'm translating left and down, and translating, and translating it down. Rotation, translation. Now, if you haven't noticed, just going to pause here for a sec. Oh, come on. It's okay. So the red and the green are reflections of one another. So the red, so this L and the other L is a reflection of one another. And actually, having too much fun here. So this blue L and the orange L are reflections of one another. So anyways, so I hope that you've seen, at least gained a good understanding of what the three things are. The next time, the next lesson will be a practice document on how to do all of these different movements across a Cartesian plane within transformational geometry. I know this seems pretty heavy, but once you start practicing, it actually isn't so bad. So I hope you enjoyed this lesson. I hope you took the notes. I'm going to also post this entire workbook on the assignment thing so that you can see it for yourself as a PDF, so you can kind of go through what I've been working on here. Okay, anyways, take care, and I will get the next lesson up and running for you shortly, probably in a couple days.